I would. All right, well, thank you and welcome back. I'm glad some of you could join us this next day. You never know what happens when you do that. I just want to make a quick announcement that for those of you that are here, and I think maybe at the end of this, either me or Christian, we can just make an announcement. I'm going to post into the chat second. Okay. So the lecture this morning, starting at 9 o'clock, that Ivan Deutsch will be giving, will be in a separate Zoom room, a Zoom webinar, and I just posted that direct link into the chat. So with that, I'll just hand it over to the students to ask questions, and Christian will be here for half an hour to do so.
Okay, so maybe just to encourage a little more, so I can, if you have questions about a specific part of the lecture yesterday, I can open the slides again and go to that part. Or if you have questions about any of the problems, then that of course would be good to ask as well.
Yeah, I should also point out that on the event webpage, the video from yesterday, as well as Christian's slides are posted, so you can open those up and look through them at this time.
Yeah, so first of all, I wanted to thank you for the nice lecture yesterday. And I wanted to ask a question about the difference between the lab and the rotating frame, because I think all the calculations we do are always done in the rotating frame, but the states in both frames differ, right? But
yes, exactly. So it's a unitary transformation that connects the lab frame to the rotating frame. And so probabilities and expectation values, observables, of course, are not affected by unitary transformation, as we know from basic quantum mechanics. You have to make a difference, though, between the rotating frame and the rotating wave approximation. So a calculation in the rotating frame, but without doing the rotating wave approximation, is fully equivalent to a calculation in the lab frame. But if you neglect those fast oscillating terms, you're making an approximation, and that is only correct if these terms are really fast. So, and that depends on the specific physics. So, for example, if you look at laser excitation, that typically is very well fulfilled, whereas if you look at microwave pulses, which are used in superconducting qubits, then this may start to break down much sooner. So in that sense, the calculations, there may be a real difference. Now, why, if the rotating wave approximation is fulfilled, why is it advantageous to go to the rotating frame? Well, exactly because you got rid of these fast oscillations. Because in the lab frame, you have the carrier frequency in the field, whereas in the rotating frame, you've transformed this carrier frequency away. So the time, if you think now of a numerical solution of your equations of motion, the time resolution that you need in the lab frame is much slower than the time resolution. The time resolution that you need in the rotating frame is much slower than the time resolution that you need in the lab frame.
okay, yeah, thank you for the answer.
Sure. A follow-up in the chat. In NMR, you usually ignore the 2 omega terms, but in QIS applications, do these affect fidelities, etc.? Well, that exactly depends on the frequencies that you're using. So if you think of quantum information applications, let's say for trapped ions or trapped atoms, where the external fields are typically optical, then you can safely ignore them and the fidelities are not affected at all. In superconducting qubits, the story is quite different, and these terms may be relevant. And we've actually seen that also in our in our own calculations. And now one thing that is interesting with respect to control is that we may do the optimization in the rotating frame, because then the control solutions are simpler also. And if we understand the strategy, then typically we find the same strategy in the rotating frame with some faster oscillations on top. But the quantitative numbers, of course, will differ. So it may be advantageous to do the optimization or to derive the control protocol in the rotating frame, even if you have to, in the end, add a correction in order to account for the fast terms that you would neglect in the rotating wave approximation. Okay, further questions?
Hi, this is Stephanie. I have a question. I was wondering if you can comment on existence of the solutions to the optimal control problem for maybe general Hamiltonians, or what are conditions?
Okay, now very good question, and you're asking actually two questions, because one is, does a solution exist? One, and then if one exists, do we have more than one or just one? And the answer to the first question, can we expect at all a solution to exist? That is something that one can answer with a mathematical theory of controllability analysis. At least in principle, because this theory is very well developed for closed quantum systems, because you have to construct the Lie algebra and then analyze for either for complete controllability, and then the Lie algebra has to be full rank, so the same size as your Hilbert space, or you have to look at specific transitions that you want to do and check if your Hamiltonian can actually generate those evolutions. Now let's assume that your Hamiltonian has all the transitions that you need in order to realize a specific target. Then the question is there one solution or more? And typically there is more than one solution. So the solution is not unique. But how many of those you will find in a numerical optimization, which always is a local search, depends on exactly how you pose the problem. So how much resources, in parentheses, you give to the algorithm. So in terms of time, in terms of amplitude, in terms of including additional constraints. That's a short version of this answer. And if you have specific points that you want me to elaborate, then please let me know. I can go on.
Is there also a theory for open systems, for existence of solutions of open systems?
So there is some developments for Markovian dynamics, so systems with Markovian dynamics, which are described by a master equation, and then we don't have Lie groups anymore that correspond to our unitary dynamics, but instead we can, or this can be visualized in terms of Lie wedges. And you have to check, for example, whether the state or the area in Hilbert space to which you want to go, whether this is part of your Lie wedge. And if you're interested, there is a bit of work on this by people like Gunther Dürr and Thomas Schulte-Herbrücken. So Thomas Schulte-Herbrücken is also the co-author of a review on this leaf-edge theory, which was a report on mathematical physics, I believe, something like this. But the name Schulte-Herbrücken is unique enough. I'll type it in the chat. It's not like Koch or Günther that you'll be able to find it.
Thank you very much.
But so just maybe to close the remark. So for systems with Markovian dynamics, there is a bit of rigorous theory. For general open quantum system dynamics, it's a completely open question. And I think we don't even have a tool yet to really tackle that problem. So I think one has to modify the notion of what do we mean by controllability. But I know that some people in France are started to think in that direction, but so far nothing tangible yet.
Mm-hmm. Thanks. And maybe a follow-up question then on the uniqueness, if I may.
Mm-hmm, sure.
What type of constraints do you apply to make the numerical optimization problem more well posed in that case? I guess if it's not unique, then the optimizer might have problems converging.
Oh.
Do you do any additional constraints to kind of tell the optimizer, or this is the solution that I'm preferring?
So I think in pretty much any optimization that I am aware of, there is some sort of either amplitude constraint or real regularization. So minimizing either the amplitude of the field or the derivative of the amplitude of the field. And that takes care of the well-posedness of the problem. And then you can add restrictions on bandwidth. You can add restrictions on avoiding certain regions in Hilbert space. So it's really, I mean, apart from this regularization, it's a matter of what you deem reasonable or desirable in terms of the physical constraints that you have for a given experiment, for example. But I would say spectral constraints and amplitude constraints are, of course, the most obvious ones.
Mm-hmm. Thanks.
So these were very advanced questions. If some of you have questions on the first part of the lecture, which were more the basics and underlying concepts, don't be shy to ask those as well.
Hi, Christian, if I may. So I asked the question about grape yesterday.
Mm-hmm.
Thank you for your answer, but I was still wondering, like, it seems the way you've mentioned it, that grape could also work for most of what you said. So particularly, what was the reason for you considering Krotov? Did it actually show something, some kind of speed up over grape for the kind of problems you were considering?
So there is a historical answer to that, and then there is a physics answer. So I knew the Krotov's method way before the grape paper was written, because it had been used in the chemistry community before. So that's the historical answer, which maybe to you is not quite as relevant. So out of the applications that I mentioned yesterday, the one where we target an arbitrary perfect entangler, that I would not know how to do with grape. If you want to optimize for a specific gate or for a state-to-state transfer, that you could easily equally do with grape.
Yeah, just to give you some background, actually, from contrary to what it might seem, I'm not actually a big fan of grape myself. It's just the thing that's built into Qtip, so I've been using it. And I've been kind of trying to find an excuse to use Krotov, but so far it doesn't seem to give me any kind of speed up or anything like that for some of the problems I'm considering. So yeah, I am on the lookout for, I don't know, some kind of physically motivated reason to maybe use something other than grape? That's really the background to my question, really.
Okay, so I think grape is actually, it's quite a performant method. The problem is not with the method itself, but it's with the implementation in Qtip, which is not the best one, not the most efficient one. So I haven't done those benchmarks, but there have been benchmarks in the past that compared grape and Kotov, and indeed found that for problems where you can use both, that the initial convergence of Kotov is significantly faster. So that's one point. And again, if you design a functional which is not quadratic in the states, then I think grape is not easy to adapt to such a function.
What would you say about scalability? Those for instance, if you have like something which, say, for 4 spins or 3 spins or a few number of qubits works equally well for Kotov and grape, do you think we would see differences if we say scale up to a lot more, like 20 spins or maybe 20 qubits or so on?
Probably not, because again, the underlying math is just very, very similar. And it's mainly in just the sequential versus concurrent update. And the numerical cost in that case is due to propagating the equation of motion. And that's the same, no matter whether you calculate your update via Kotov or via grape. And of course, also the question of scalability of control. So can you use a control that you obtain with 3 or 4 qubits to a calculation with 10? Probably not, because I mean, there you would have to one could think of doing an optimization where you simultaneously optimize with n qubits and n+1 qubits and try to find a pulse that works equally well for both. But I'm not sure that I mean, it's something that one could try, but I haven't.
But what about spins, for instance? If you forget about qubits, what if you just consider, say, nuclear spins? Say something if we have something with controlling 4 nuclear spins, would that also be would that also not guarantee that this would work for maybe 10 or 12 nuclear spins, for instance?
Well. So again, the optimization algorithm gives you what you're asked for. Mm-hmm. So if you do the optimization with a fixed number of spins, you get an answer that works for this fixed number of spins, but there's no guarantee it will work for a different number of spins. So if you want it to work for a different number of spins, you somehow have to tell the algorithm that this is a property that you desire. And you have to think, how mathematically can you encode that criterion in your functional? And again, the brute force way would be to just say, let's do an ensemble optimization where I use the same control to drive 4 spins and to drive, I don't know, 6 spins. And can I find with these 2 different Hamiltonians and the same control talking to both, can I find a compromised control that does the job in both setups, in both systems? But you're not guaranteed to get an answer. I mean, but it's definitely worthwhile to try.
Oh, thank you. Also, I wonder if you because I've been looking into all of these methods. There's one method which has recently gained a bit of traction. It's a C++ framework called Quandary, and what they use is trajectory optimization. I wonder if you have any comments on that.
What do you exactly mean by trajectory optimization?
So they use some kind of trajectory optimization to essentially do what grape does, and they claim speed up over grape and Kotov, but it's not a paper I understand very well. So
trajectory optimization in the sense of Monte Carlo wave functions, that you do an unraveling of the master equation, or?
Probably. I don't exactly remember, but essentially they were trying to find something that outperforms Kotov and grape. And they've done some, I think the paper's title is optimization via quantum trajectory optimization or something. Yeah, and they use a combination of Julia and the C++ to try to
Well, again, I mean, there is one very obvious way how you can improve in terms of the optimization, and that is by including information, not just of the gradient of your optimization functional, which is what is done in standard grape and standard Kotov, but you also include information from the second order derivatives. And that's actually one of the advantages of grape, that you can very easily interface it with what is called LBFGS, which is
that's actually what I've been doing in my project anyway.
Okay, okay. So, but that's a way to speed up. You can also do this for Kotov. But now the question with the trajectories, I see it really as modular, right? So you have the optimal control is sort of an outer loop, and then within that loop you have to solve your equation of motion. And one way is you solve you calculate the evolution of the density operator as a function of time, or you unravel the solution of the density operator by doing this Monte Carlo stochastic trajectory approach and construct the density operator or expectation values by stochastic averages over quantum trajectories. And that is a method which is very well known, and also the scaling of it is very well known. So there is a turnover point in terms of Hilbert space dimension when this unraveling approach becomes advantageous compared to directly solving the equation of motion of the density operator. But that I don't see. I don't see how this is directly connected to the optimization. It's really. It's a matter of how to solve the equation of motion.
Okay, I've put the paper in the chat. I'm not sure if you've seen it before, but if you have any more thoughts, maybe, I don't know.
I can check. I may have seen it, but I haven't looked into it in detail. Yeah, so this is, I've heard actually Jens, by chance we are sharing the same last name, talk about this, but I don't understand enough of it to give you a good answer on that.
Yeah, that's where I am actually at this, here as well. Like, I've looked at Quandary, which was the C++ package, and it seems that grape plus BFGS is doing pretty good, and I don't think that would do anything significant apart from redoing everything in C++. And of course, what you can get with grape and BFGS, I think you can get something similar with not too much difference in performance with Krotov as well. That's what I would guess. But this is something where I don't know. Like this is probably the next thing I'm going to look at.
So here, what they're saying is they use a different way. They use this numerical differentiation.
Yes.
I'm actually a little bit skeptical that it works as well, at least in a general setting, as they claim, because
yeah, that's exactly the point. For instance, they have an example where they show some kind of fluxonium thing, and it could very well be that it's the speed up that they claim is kind of specific to their setup, right? I don't see how I can translate that to, I don't know, a system with the nuclear spins, for instance. It's not so straightforward.
So I tend to agree with you. I mean, one would have to really test the numerical framework to make firm claims. But in my experience, the accuracy of the gradient is actually important. And I would expect numerical differentiation to suffer and to be less accurate in comparison to grape or Krotov, where the gradients are calculated analytically and then approximated only via the calculation of the equation of motion.
Yeah.
Maybe I can comment here too, because it came up in Quandary, which is what I've been working on. It's not exactly what is in the paper, that's different. So in Quandary, we also, or in the Julia code, we also solve the equation of motion. The speed up there comes from parallel distribution of that. So it's targeting high performance platforms. And that's a spatial distribution. And then we do a standard BFGS on that gradients using automatic differentiation. And I think that goes back to the question then, how exact should a gradient be?
Mhm.
With automatic differentiation, that's exact on the implementation level. So whatever you implement to evaluate the objective function, that's gradient you're going to get, versus an analytic gradient, which is exact in the limit of smaller and smaller time steps. We haven't done a direct comparison in terms of optimization, but since all of those are basically BFGS type of algorithms, I'm expecting their, in terms of optimization convergence, to be fairly similar.
Mm-hmm. Yeah, I agree with Stephanie, and for the specific case of spin, since you were mentioning it, there has been a paper a couple of years ago, maybe something like 8 or 10, by Ilya Kuprov, on the role of the accuracy of the gradient for grape. So you may want to check that out to get some more insight.
Thank you.
Okay, then there is a question in the chat that I get all the time, no matter where I teach. So our students in Berlin like to ask that question, do we get solutions? And the answer is no. We have the solutions. We know that the problem is solvable with the information that's there, but no, we don't give out solutions, because that's what it, in the end, what it takes to be a physicist. You learn how to solve problems. So you can get advice if you're completely stuck. Feel free to get in touch, and I'll, in particular, the problems that I gave on the first part, I have just used in the past semester in the course I was teaching here in Berlin. So I can, if I don't have time to answer myself, I'll forward them to my TA, and he'll be happy to help you. But no complete solutions.
Hi, just to jump in, this room can continue going if you want to continue the discussion. I'm going to sign off and start the webinar watch party here, but please feel free to stay and continue the discussion. Thank you.
Okay, thanks, Carolyn. So we have another question about the rotating frame. And so please, everybody, feel free to go to Ivan's lecture. I'm sure it will be very interesting, but I'll still answer to Anupam Mitra for the question on the unitary. Well, yes, the gate is not the same, because again, the two frames are connected by unitary transformation. And only things that you measure should be the same and are the same. Say if you make the rotating wave approximation, so then of course you may expect differences. But and also, of course, the controls that you calculate depend on the frame. So if you transform away the carrier frequency with which your frame rotates, then and you want to use the field in an actual lab, in an actual experiment, you better make sure that you somehow phase this in again. But even, I mean, if you remember the one example from experiment I showed you with our friends in Paris, so they actually synthesized the amplitude modulations in the rotating frame, and then mixed in the experiment, mixed in the carrier frequency afterwards, after the modulation. So they also can work in the rotating frame, and just make sure when they send the field to the atom, then it should have the frequency mixed in. Okay, so bye everybody. Enjoy Ivan's lecture. just in case that you were expecting to see the lecture here, let me repost that this was just the Zoom room for the Q&A to my lecture from yesterday. And today's lecture is in the Zoom room that I've just posted in the chat. Okay, I think the 3 remaining students, do you still have questions? I'll be happy to answer. But if you're here by mistake, because this is the wrong Zoom room, then maybe we should close this room.
Yes, I think this is finished. Thank you, Christine.
Okay, thanks, Matteo.
Thank you.
Bye-bye.
Bye.